Welcome to the Research Cortex's AACTO Abridged, where we summarize our published works. In this edition, we give an overview of Dr. Rachel Traylor's paper, A Generalized Multinomial Distribution from Dependent Categorical Random Variables. In a nutshell, what does this paper do? First, it studies the effect of relaxing the assumption of independence within a series of categorical random variables. Second, it shows that, for a particular kind of dependence, the random variables in the sequence remain identically distributed. And third, it uses this to create a more general multinomial distribution that handles correlated categorical random variables, and we'll address each of these three in depth. First, what do we mean by a categorical random variable? Most of you are at least intuitively familiar with the concept of a special form of this, the Bernoulli random variable. A Bernoulli random variable takes on values 1 and 0 for success or failure. Now suppose I have two choices for lunch, a ham sandwich and a cheeseburger. Without any loss of generality, let the ham sandwich be represented by 1. We consider a ham sandwich a success, and 0 represent the cheeseburger. Then a Bernoulli random variable with probability p gives the probability that a random person selects a ham sandwich for lunch. The probability that he selects the cheeseburger is given by q, which is equal to 1 minus p. Now suppose that we have more than two choices for lunch. Then we will represent this by a categorical random variable with k categories. So we represent this formally by a categorical variable with vector probability p, and there are k possible probabilities, one probability for each category. Now suppose, for an example, we now have four choices for lunch: the ham sandwich, the cheeseburger, a Caesar salad, and French onion soup. Then the probability of selecting the ham sandwich is given by P1, the selection for cheeseburger P2, the probability for salad P3, and the French onion soup P4. Now, implicitly, we have numbered these categories 1, 2, 3, and 4. We can just as easily have labeled them A, B, C, and D. The point here is that they are categorical, not ordinal, not numeric. So the probability of selection is actually the probability of just selecting that category, not the probability that we have selected the integer 1. Now, suppose n people in sequence make their choices for lunch. Let's revisit the binary choice option to keep things simple. I would like to know how many people selected the ham sandwich. More simply, I would like to know the number of successes, or 1s, in the sequence of Bernoulli variables of length n. So, let's call the Bernoulli random variables epsilon I, where I goes from 1 to n, and epsilon I takes on the values 0 and 1, and the sequence is Bernoulli distributed with probability p. Now, if we want to know the number of successes in the sequence, so how many of these people selected the ham sandwich, let's call that random variable x. So this is the number of people who ate a ham sandwich. So x is going to count the number of 1s, and this is actually a function of the epsilons, and formally we may express this as the sum of epsilon I. Now why is that the case? Because if epsilon I is 0 or 1, then the number of 1s counts the number of people who ate the ham sandwich, and hence the sum of those tells me the number of people. Then we say that x has a binomial distribution with n Bernoulli variables, n trials, with probability of success p. And the PDF of x, or the probability that x is equal to some observed little x, the number of successes, is going to be equal to little n, choose x, times p to the x, times 1 minus p to the n minus x. Just as the categorical random variable was a generalization of the Bernoulli random variable, the multinomial distribution is a generalization of the binomial distribution. The multinomial distribution is built from categorical variables in a very similar way to the binomial distribution being built from Bernoulli random variables. So now, given that n people made their choices for lunch when there are more than 2 options, how many of those n chose the ham sandwich? How many chose the cheeseburger, the salad, and the soup? The equation for this is given by f of x1 to xk, where k represents the number of categories, and there are n in our sequence, and there are k different probabilities of selection, and this is given by n factorial divided by x1 factorial, x2 factorial, and so forth to xk factorial, times p1 to the x1, p2 to the x2, so forth, pk to the xk. Now that first coefficient out in front is called the multinomial coefficient, and this represents the probability that a vector x, which takes on values x1, x2, all the way to xk, so how many categories are there, is equal to little x1 through little xk, where these are observed values. So that's what this represents. Suppose, for an explicit example, that the probability of selecting the ham sandwich is 1/8. The probability of selecting the cheeseburger is also an 1/8. The probability of selecting the salad is 1/4, and apparently this place has really good French onion soup, so the probability of selecting that is 1/2. So suppose explicitly, let n equal 10. We have 10 people. Now, I want to know what the probability is of those 10 people. 5 of them select the ham sandwich, 3 select the cheeseburger, 1 selects salad, and 1 selects the French onion soup. Then we can find that by 10 factorial divided by 5 factorial, 3 factorial, 1 factorial, 1 factorial, times p1, which is 1/8, and there were 5 that selected this one, times p2, 1/8, 3 that selected this one, and so forth. And this is the probability that if 10 people come through, you will have this arrangement of selections. Now, the key assumption in moving from the categorical to the multinomial distribution is the notion of independence. That is, as we move down the sequence where people get to choose their option for lunch, one person's selection doesn't affect anyone else's. Now, in reality, this may or may not always be true. So this paper aims to relax the assumption of independence and see what happens. We'll start with the simplest notion of dependence, first detailed by Andrzej Korzenowski in 2013. We call this type first-kind dependence, in that we alter the selection probability of the second person's options, and so forth, in favor of whatever the first person selected, and compensate by decreasing the other probabilities. Remember that the selection probabilities must always sum to 1. We can represent all of the possible sequences by a binary tree, where each level of the tree represents a Bernoulli random variable. Suppose we're just going to look at 3 for the sake of simplicity. So here, the first one can make a selection of a 0 or a 1, a ham sandwich or not a ham sandwich. Now, after that, the second one goes, and he can make a selection of 1 or 0 as well, but if we're keeping track of people as they go through the lunch line, it matters what the first one did. So if the first one selected a 1, it doesn't change the choices of the second. So he can either select a 1 or a 0, just as if he did not select the ham sandwich, he can select a 1 or a 0. Likewise, when the third guy comes around, we keep track of who came before and what their selection was by creating child nodes off of each parent node, like this. Now remember each one of these. So this is the first variable, or the first person. There's the second person, and here's the third person. So this way you can actually see all of the possible sequences of length 3 when there are two choices for lunch. The first person could select the ham sandwich, the second person could select the ham sandwich, and the third person could also select the ham sandwich, in which case you would end up with the sequence 1, 1, 1. Similarly, if only one person selected the ham sandwich and he was the first one, then the sequence 1, 0, 0, tracing down the tree, would give you that scenario. Recall that the probability of the first person selecting a ham sandwich, given this way, is given by little p. If all of the variables were independent, then given the selection of the first person, the second person's probability of the ham sandwich would also be p. Now, we're not going to assume that anymore. Let's relax that and assume that the second and third person are more likely to select the option that the first person did. We're going to increase their conditional probabilities by a factor of delta times 1 minus p, and then subsequently decrease the probability of them selecting a different option by the same factor. So let us now define the following quantities. P plus is going to be p plus delta times q. Remember that q is 1 minus p. Q minus is equal to q minus delta q. Remember that p plus q is equal to 1. So if I adjust p by a factor, I must adjust q by the negative of that same factor. Similarly, I'm going to define q plus is equal to q plus delta p, and p minus is equal to p minus delta p. Now, delta is any number between 0 and 1. So what does this actually mean? Let's look at what this means. The first person can select the ham sandwich with probability p, or the cheeseburger with probability q. Now, if all of the variables were independent, then the probability of the second person selecting the ham sandwich here would be p if the first person selected the ham sandwich, and it would also be p if the first person selected the cheeseburger. But in first-kind dependence, it matters what the first person did. So we weight towards what the first person did and away from selecting what he did not. So similarly, then we have to adjust this way. The third person, same thing. We actually, in this type of dependence, don't care what the second person did, and we actually weight towards what the first person did. So if the first person selected a ham sandwich, then the probability of the third person selecting the ham sandwich is p plus, and similarly. So note here that it doesn't matter what the second one did, only that the first person had selected the ham sandwich. And this is Dr. Korzenowski's notion of first-kind dependence. Now this is easily transferred to categorical random variables simply by making a 3-node tree, a canary tree instead of a binary tree. Let's get a little bit more familiar with this and look at the extremes. So remember that delta takes values between 0 and 1. What this actually represents is if delta is 0, then all of the variables in the sequence are independent. So let's take a look at that. If delta is 0, then what happens? Delta q becomes 0, delta p becomes 0. So that means that p plus and p minus are just p again, q plus and q minus are just q again, and you're back to what we had before. Now, on the other end of the extreme, if delta is 1, then what does that mean? Well, we already know that, remember that p plus q is equal to 1. So if delta is equal to 1, then p plus would actually be equal to 1. Q minus would be equal to 0. P minus would be equal to 0. And q plus would be equal to 1. Now, what does that bear out here? What that actually means is that the first one has a probability of selecting the ham sandwich p or q. But the second, third, fourth, etc., those are no longer random. That means if they are completely dependent on what the first person did, then their selection is completely deterministic. So for example, if your boss is the first one and everyone is completely dependent on what your boss selects for lunch, if your boss selects the ham sandwich, then every person that follows him will select the ham sandwich. On the other end, if it's just a bunch of random people in line at a deli, Perhaps they don't depend on each other at all, and delta is 0. In that case, the probability of the second person selecting the ham sandwich doesn't change, given the selection of the first one. So what was done in this paper? Well, we did do the example of first-kind dependence for binomial, but it generalizes easily to the categorical random variable. We proved that the first-kind dependent categorical variables are still identically distributed. What that means is that even though there is a dependence of the second, third, fourth, etc. on the first one, the probability that epsilon j is equal to some category k is still little pk, where j being a subsequent person after the first one. So they're actually still identically distributed. We actually needed that because we're going to use that later for to look at the generalized multinomial distribution. The next thing in the paper was the derivation of the cross-covariance matrix, which is a generalized version of the covariance between any two categorical random variables. Now I won't go into details of that on this video. The paper is freely available if you want to read that. Because the dependent categorical variables remained identically distributed, then we may now give an explicit probability distribution for the number of people who selected each lunch option when their choices depend on the first person's selection. The interesting thing about the equation I've given here is that if you pick it apart, it's really just the sum of a probability times different standard multinomial distributions. So in mathematical terms, we would call this formula quite natural. So let's look at an explicit example. Let's return to the 4 category selection options for lunch with the same probabilities that we used before. So the ham sandwich has a probability of 1/8, the cheeseburger has a probability of 1/8, the salad a probability of 1/4, and the French onion soup a probability of 1/2. Now, suppose that the selection sequence has first-kind dependence, but not total dependence. Let's let the dependency coefficient delta be 1/2. Now we want to know what the probability is that if 10 people come through, that 5 select the ham sandwich, 3 select the cheeseburger, 1 selects the salad, and 1 selects the French onion soup. Let's run through a quick example of how the probabilities may change. Now, P1 plus would be given by P1 plus delta times P2 plus P3 plus P4, very similar to how we did the Bernoulli case and the binomial case. So this would be equal to 1/8 plus 1/2 times 7/8. So if the first person selects the ham sandwich, then the probability of the second person selecting the ham sandwich and the third person and so forth has actually been increased by a factor of 7/16. Now, if the first person does not select the ham sandwich, then the probability of the second person, the third person, and so forth actually selecting the ham sandwich, going against what the first person did, is going to be given by P1 minus delta times P1, which is 1/8 minus 1/2 times 1/8, which is equal to 1/8 minus 1/16, which is 1/16. So here I have calculated all of the new weighted probabilities, P1 plus, P1 minus, P2 plus, P1, P2 minus, etc. And now, if we want to know under these conditions, what is the probability that if 10 people come through the line with first-kind dependence, that 5 select the ham sandwich, 3 select the cheeseburger, 1 selects the salad, and 1 selects the French onion soup? It's given using the equation. So the first person selects the first option, being the ham sandwich. That probability is 1/8. Now there are 9 people left. So 9 people can select, 4 of which can select the ham sandwich, 3 of which can select the cheeseburger, 1 the salad, and 1 the soup, times the weighted now probabilities raised to their respective powers. So P1 plus, because the first one selected the ham sandwich, to the 4th, P2 minus to the 3rd, P3 minus to the 1, and P4 minus to the 1. Similarly, we Now, what if the first person selects the second option? And we proceed in a similar fashion, and this is the explicit way to calculate the probability of this sequence under first-kind dependence conditions. Some other interesting key results of this paper is that now that the generalized multinomial distribution has been derived, the marginal distributions were given. In addition, the moment generating function was derived. This allows the mean in the covariance matrix to be easily obtained. The third thing is that an algorithm to generate a sequence of first-kind dependent categorical random variables is given. Now, I'm not going to go into detail in this video of all three of these other key results. You're welcome to read the paper to get further details. This has been another edition of AACTO Abridged, in which we discussed a generalized multinomial distribution from dependent categorical random variables by Dr. Rachel Traylor.